On a clear night, the farthest object visible to the human eye without a telescope is the Andromeda Galaxy. Not a star, a galaxy containing roughly 1 trillion stars spread across more than 200,000 light years of space. The light reaching Earth tonight left Andromeda approximately 2,537,000 years ago, long before modern humans existed. And despite being the closest large galaxy to the Milky Way, Andromeda may be permanently unreachable, not because humanity lacks advanced enough technology, because the laws of physics themselves appear to prevent the journey. The speed of light is the fastest speed anything can travel in the universe, 299,792 kilometers per second. At that speed, light reaches the moon in just over 1 second. It reaches the sun in 8 minutes. It crosses the Milky Way in roughly 100,000 years, and it still takes more than 2 million years to reach Andromeda. But relativity creates an even larger problem. According to Einstein's equations, any object with mass requires more energy the faster it moves. As a spacecraft approaches the speed of light, the energy required rises toward infinity, which means no human spacecraft can ever truly reach light speed at all. And if a crew somehow came close, time itself would begin separating them from Earth. Years aboard the ship could correspond to millions of years passing outside it. Entire civilizations could disappear before the travelers ever arrived at their destination. At the same time, the universe itself is expanding. Space between galaxies is stretching continuously, carrying distant regions farther apart faster than any spacecraft could realistically travel. Some parts of the universe are already permanently unreachable, not because of engineering limits, but because space-time itself no longer allows contact. Andromeda sits close enough to remain gravitationally connected to the Milky Way, but everything beyond it begins disappearing behind distances humanity may never overcome. If you enjoy documentaries exploring the deeper side of space and physics, consider subscribing. It genuinely helps support the channel and future videos like this. Let's talk about what the universe actually allows. Long before anyone understood what galaxies were, observers simply described what they could see. In the year 964, the Persian astronomer Abd al-Rahman al-Sufi recorded a faint object in the constellation Andromeda and called it a little cloud. That was all it appeared to be, a soft blur, a pale stain against the dark. Centuries later, in 1771, Charles Messier formally catalogued it as Messier 31 while compiling objects that might confuse comet hunters. Even then, nobody imagined they were looking beyond the Milky Way itself. For nearly 1,000 years, every astronomer who studied Andromeda assumed it belonged to our own galaxy, suspended somewhere inside the familiar river of stars surrounding Earth. The uncertainty lasted into the 20th century. Telescopes improved, photographic plates sharpened, but the scale of the universe remained deeply unclear. In 1920, astronomy reached a turning point known as the Great Debate. Harlow Shapley argued that the Milky Way encompassed the entire universe, and that Andromeda was merely a nearby nebula drifting inside it. Heber Curtis disagreed. He believed Andromeda was an island universe, a separate galaxy unimaginably far away. The disagreement was not technical trivia. Everything depended on the answer. If Curtis was correct, the cosmos was vastly larger than humanity had ever conceived. 3 years later, Edwin Hubble settled the question from Mount Wilson Observatory in California. He identified a Cepheid variable star inside Andromeda. Cepheid variables brighten and dim in regular cycles, and astronomers can use those cycles to determine their true brightness. Once the true brightness is known, distance can be calculated by comparing it to how dim the star appears from Earth. Hubble's measurements showed Andromeda was far outside the Milky Way. His original estimate placed it roughly 900,000 light years away. Later instruments revealed the true distance, approximately 2.537 million light years. The universe changed overnight. Not physically, but conceptually. The Milky Way stopped being the whole of existence and became one galaxy among countless others scattered across unimaginable depths. Andromeda itself is immense. Its visible diameter stretches roughly 220,000 light years, nearly twice the width of the Milky Way. It contains around 1 trillion stars, several times more than our own galaxy's estimated 300 to 400 billion. Its age is approximately 10 billion years, older than the Milky Way by more than a billion years. And despite the scale involved, its distance has now been measured to within roughly 1% precision. We know its structure, mass, age, motion, and history. We know the behavior of stars inside it. We know a black hole waits at its center. But we know all of this while remaining completely separated from it, fixed here beneath our own sky. And once that settles in, another question quietly appears. What would it actually take to go there? 299,792 kilometers per second, 186,000 miles per second. The number arrives almost too large to attach meaning to, so physics forces us to shrink it into smaller moments. In a single second, light circles Earth roughly 7.5 times. It touches the moon in 1.3 seconds. Sunlight reaches your skin after traveling 8 minutes and 20 seconds across the solar system. Beyond that, the distances begin unfolding into years instead of miles. Light needs 4.24 years to reach Proxima Centauri, the nearest star beyond our Sun. To cross the visible width of the Milky Way, it would continue for roughly 100,000 years, and still, Andromeda remains farther away. Even traveling at light speed, the crossing would require approximately 2.537 million years, minimum. That word matters. It assumes the distance remains fixed while the journey unfolds. It does not. Space itself changes while light travels through it. But before we reach that complication, we have to understand why this speed stands where it does, untouched by every engine, every ambition, every imagined machine. In 1865, the Scottish physicist James Clerk Maxwell assembled a set of equations describing electricity and magnetism as parts of the same underlying phenomenon. The equations produced an unexpected answer. Electromagnetic waves, including visible light, always moved through empty space at one fixed speed. The source did not matter. The motion of the observer did not matter. The number remained constant. For decades, nobody understood why. Then, in 1905, Albert Einstein accepted the number exactly as nature presented it. Instead of treating the speed of light as a measurement needing explanation, he treated it as a foundation. From that decision came special relativity, the realization that space and time are not rigid backgrounds, but connected parts of a single structure called spacetime. Distance changes, time changes. Simultaneity itself changes depending on motion, but the speed of light does not. The consequences feel almost impossible at first encounter. Imagine standing inside a spacecraft already moving at 99% the speed of light. You point a laser forward and activate it. Intuition says the beam should move ahead at 199% light speed relative to Earth. It does not. Every observer, inside or outside the ship, still measures the beam moving at c, the universal shorthand for light speed. Something else bends instead. Space contracts. Time dilates. Measurements rearrange themselves around the constant. This is not a flaw in our instruments or a temporary gap in understanding. The speed of light is woven into the structure of reality itself. More precisely, it is the speed of causality, the maximum rate at which any event can influence another anywhere in the universe. We know the limit now. The harder truth is what happens when matter tries to approach it. Inside the tunnels beneath the French and Swiss countryside, protons spend hours accelerating through a circular machine 17 miles wide. The machine is the Large Hadron Collider, the most powerful particle accelerator humanity has ever constructed. By the time those particles approach their maximum velocity, they are moving at approximately 99.999999% the speed of light. At that speed, something strange begins to happen. The protons resist acceleration far more strongly than they did at rest. Not slightly, dramatically. They behave as though they are 7,461 times heavier than their ordinary mass. This effect comes directly from Einstein's special relativity. In 1905, the theory revealed that mass and motion are tied together far more deeply than classical physics assumed. As an object with mass accelerates, its relativistic mass increases. In simple terms, the faster it moves, the harder it becomes to push faster still. Every increase in velocity demands more energy than the increase before it. At lower speeds, this barely matters. Cars, aircraft, and planets move slowly enough that relativity remains invisible. But near light speed, the equations begin tightening like a vise. To reach 10% light speed would require extraordinary energy, yet still exists within theoretical discussion. 50% demands vastly more. 90% becomes extreme. 99% enters a region where the required energy rises by orders of magnitude for tiny additional gains in speed. Then the curve breaks completely. To reach exactly 100% light speed, an object with mass would require infinite energy. Not enormous energy, infinite. The mathematics do not produce a larger engine waiting somewhere in the future. They produce a wall. Infinite energy does not physically exist within the universe. Because of this, light speed is not a technological challenge awaiting solution. It is a mathematical limit built directly into spacetime itself. Only particles without mass can travel at exactly c, the shorthand physicists use for the speed of light. Photons, the particles of light itself, exist permanently at that speed. They cannot slow down. They cannot speed up. They simply move through the universe at the maximum rate causality permits. A spacecraft cannot do this. No matter how advanced its materials become, it still contains mass. Every astronaut, every shield plate, every fuel tank adds to the burden. The ship may creep closer and closer to light speed, but the closer it moves, the more violently physics resists further acceleration. The gains shrink, the costs explode. Even our current achievements remain tiny against the scale involved. The fastest human made object ever constructed, NASA's Parker Solar Probe, reached approximately 690,000 kilometers per hour while diving close to the Sun. That sounds overwhelming until translated into relativistic terms. It is only about 0.064% light speed. At that velocity, a journey to Andromeda would last roughly 4 billion years, longer than Earth has existed as a planet with complex life. But imagine we somehow overcame this and approached 99% light speed anyway. The travel time appears to collapse. The galaxy seems almost within reach. Yet something else begins distorting instead. Something far stranger than mass or energy, time itself. Every second on Earth is not the same everywhere. Time changes its pace depending on motion, and modern civilization quietly accounts for this every day. The satellites guiding your phone's navigation system orbit Earth at roughly 14,000 kilometers per hour. Their clocks tick slightly differently from clocks on the ground. Specifically, they gain about 7 microseconds each day due to relativistic effects. A microsecond is 1 millionth of a second. Tiny, barely imaginable. But if engineers ignored those differences, global positioning systems would drift by kilometers within a single day. The universe measures time carefully. Far above Earth's atmosphere, another experiment unfolds continuously without human intervention. Cosmic rays, high energy particles arriving from distant space, strike atoms in the upper atmosphere and create particles called muons. Muons are unstable subatomic particles with a natural lifespan of only 2.2 microseconds. At rest, they should vanish long before crossing 15 kilometers of atmosphere to reach the ground. Yet they do reach the ground in enormous numbers every second. They survive because they move close to light speed. From our perspective, their internal clocks slow dramatically. The process is called time dilation. Time itself stretches for the moving particle. What should have been a brief existence becomes long enough for the muons to continue downward through the atmosphere before decaying. This is not speculative physics. It is measured constantly, repeatable in laboratories and particle detectors across the world. Einstein's equations describe the effect precisely through something called the Lorentz factor, a formula determining how much time slows at a given velocity. At 99% light speed, time passes roughly 7 times slower for the traveler than for someone standing still. At 99.9%, it slows by about 22 times. At 99.999%, the factor rises to approximately 707. Push closer still, toward 99.999999%, and the difference climbs into the thousands. From inside the ship, the journey compresses. A traveler moving at extreme relativistic speed might personally experience only a few centuries crossing the gulf toward Andromeda. Their heartbeat continues normally, their thoughts unfold normally. Meals are eaten, conversations happen, years pass inside the vessel, but outside the ship, the universe advances almost untouched by their slowed perception. 2.537 million years pass on Earth. The traveler arrives carrying memories of a civilization erased long before arrival. Continents have shifted, languages disappeared, every monument collapsed into geology, entire species evolved or vanished. The stars familiar at departure no longer occupy the same positions in the sky. Even the mission itself may survive nowhere except the mind of the person who endured it, but the traveler still feels the separation. More intensely now, time dilation does not rescue the journey from isolation, it amplifies it. The faster you move, the more completely you detach from the era that launched you. Velocity becomes a kind of exile. You reach the destination by abandoning the world behind almost entirely. And even this imagined crossing assumes those extraordinary speeds can somehow be achieved. The equations allow the clock to slow. They say nothing about survival because long before a ship approaches Andromeda, space itself begins turning hostile to the human body. A glass vacuum chamber on Earth feels empty because almost every particle has been removed from it. Space seems emptier still. Between stars, and especially between galaxies, darkness appears absolute to human senses. But the emptiness is incomplete. The universe never fully clears itself. Every region of space contains a thin scattering of matter called the interstellar medium. It is a diffuse mixture of hydrogen atoms, helium, dust grains, free electrons, and charged particles drifting between stars. Inside the Milky Way, The average density is roughly 1 atom per cubic centimeter. By earthly standards, that is almost nothing. Between galaxies, the intergalactic medium becomes thinner still, falling to approximately 1 atom per cubic meter across the enormous voids separating galactic systems. At ordinary velocities, these particles barely matter. Spacecraft already traveling through the solar system pass through them continuously without consequence. But relativity changes the interaction completely. Speed transforms harmless material into radiation and impact energy of terrifying intensity. In 2012, physicist William Edelstein and his research team examined what would happen to a spacecraft approaching 99.99% light speed through interstellar space. At those velocities, even isolated hydrogen atoms striking the front of the ship would hit with energies comparable to proton beams used in cancer treatment facilities on Earth. Except these impacts would occur not inside controlled hospital equipment, but continuously across the entire forward surface of the vessel. The radiation dose becomes catastrophic almost immediately. At 99.99% light speed, the estimated exposure inside an inadequately shielded spacecraft reaches roughly 10,000 sieverts per second. A sievert is a unit measuring the biological damage caused by radiation exposure. Around 6 sieverts total is generally lethal to a human being. The relativistic spacecraft exceeds that threshold in a fraction of a second. So the ship requires shielding, thick shielding, dense enough to absorb high-energy particle impacts across millions of years of travel. But shielding creates another problem because shielding has mass, and mass demands additional energy to accelerate. More shielding requires more fuel. More fuel adds more mass. The equations begin feeding back into themselves again. Then the dust arrives. A grain of interstellar dust, only 1 millimeter wide, appears insignificant at rest. At 99% light speed, its kinetic energy, meaning the energy carried by motion, rises to levels comparable to a small explosive device. Every collision becomes violent. Every impact carries the potential to puncture, vaporize, or irradiate sections of the ship, and the spacecraft cannot simply endure occasional strikes. It must survive uninterrupted bombardment across 2.537 million light years. The navigation systems, therefore, inherit an impossible responsibility. Forward sensors would need to detect and deflect particles continuously, without failure, across distances larger than civilizations, species, and geological eras combined. One missed object could destroy the mission instantly. At relativistic speed, space stops behaving like a silent void. It becomes a storm of invisible projectiles arriving with nuclear intensity. The body cannot survive unprotected exposure. The ship cannot practically carry the shielding required. And underneath all of it waits another problem still unresolved, because accelerating any vessel to these speeds demands energy on scales almost detached from comprehension itself. At the heart of every rocket launch sits a deceptively simple equation written in 1897 by the Russian physicist Konstantin Tsiolkovsky. The equation describes propulsion itself. To move faster, a spacecraft must carry more fuel, but fuel has mass, and that mass must also be accelerated, which requires still more fuel. The relationship grows exponentially. Each increase in desired velocity expands the required propellant far beyond intuitive scales. Chemical rockets already struggle against this problem inside our own solar system. Most of the Saturn V rocket that carried Apollo astronauts to the moon was fuel. The astronauts themselves occupied only a tiny fraction of the vehicle's total mass. Intergalactic travel magnifies this imbalance until the numbers begin slipping outside ordinary engineering entirely. Physicists therefore turn toward the most efficient energy source known to science: antimatter annihilation. Antimatter consists of particles identical to ordinary matter, except with opposite electric charge. When matter and antimatter meet, both disappear completely, converting their mass directly into energy according to Einstein's equation, E equals mc squared. No chemical reaction approaches this efficiency. No nuclear reactor compares to it. In theory, antimatter propulsion extracts 100% of mass as usable energy, and still it fails. Even under idealized assumptions with perfect efficiency, accelerating a 1,000 kilogram spacecraft to only 10% light speed would require roughly 100 million tons of antimatter. Humanity has never produced anything remotely close to this amount. Since antimatter was first created in laboratories during the 20th century, total human production across all facilities combined amounts to approximately 10 nanograms, enough energy to power a small light bulb for several seconds. The scale mismatch becomes difficult even to phrase. We are discussing requirements separated from our actual capabilities by factors so large they stop feeling technological and begin feeling geological. At 99% light speed, the required energy rises beyond the total output the sun will generate across its entire estimated 10 billion year lifetime, not yearly output, total lifetime output. A single relativistic spacecraft begins competing energetically with stars. Some projects still attempt smaller steps toward relativistic travel. Breakthrough Starshot, announced in 2016 and supported by physicists, including Stephen Hawking, proposes sending gram-scale probes toward Proxima Centauri using immense Earth-based lasers. Each probe would weigh roughly as much as a postage stamp and travel at approximately 20% light speed. Even those probes would need around 12.5 million years to reach Andromeda, and accelerating them requires staggering infrastructure. The proposed laser array would generate approximately 100 gigawatts of power, comparable to the simultaneous output of roughly 100 nuclear power plants focused together into a single directed beam. That effort would propel not astronauts, not habitats, not living organisms, but microscopic instruments. Scale the concept upward to a crude vessel, and the equations detach from anything the solar system could realistically supply. Reaching even 10% light speed with a human-carrying spacecraft would likely require converting the entire mass of a large asteroid directly into energy through perfect matter, antimatter annihilation. But every attempt to solve the travel problem keeps circling back toward the same barrier. Distance, radiation, time dilation, and fuel are not separate obstacles waiting for separate inventions. They emerge from the same underlying structure. The physics defining light speed also defines the impossible cost of approaching it. Imagine drawing two dots on the surface of a balloon, then slowly inflating it. The dots are not crawling across the rubber. The rubber itself stretches, carrying the dots apart without either one actively moving away from the other. Modern cosmology describes the universe in much the same way. Galaxies drift apart not primarily because they travel through static space, but because space itself expands between them. Edwin Hubble uncovered this in 1929 while studying the light from distant galaxies. Their light appeared shifted toward red wavelengths, an effect called redshift, indicating recession. More surprisingly, the farther a galaxy stood from Earth, the faster it receded. The relationship became known as the Hubble constant, roughly 70 kilometers per second for every megaparsec of distance. With 1 megaparsec equal to approximately 3.26 million light years. The implication altered the structure of reality again. The universe was not fixed. Every large-scale region was separating from every other region simultaneously. Andromeda occupies an unusual position inside this expansion. Its gravity and the gravity of the Milky Way bind the two galaxies together strongly enough to overcome the outward stretching of space locally. Instead of receding, Andromeda approaches us at roughly 110 kilometers per second. The galaxies are already falling toward each other through their shared gravitational attraction. But beyond our immediate neighborhood, the expansion dominates almost everything. The Milky Way belongs to a collection called the Local Group, approximately 54 galaxies bound together gravitationally. Outside that structure, distances grow steadily larger over cosmic time. Eventually, the expansion reaches a threshold where separation happens faster than light itself can cross the intervening space. This boundary is called the cosmological horizon, or Hubble sphere, lying approximately 14.5 billion light years from Earth. Beyond that limit, galaxies become permanently unreachable, not because their current distance is too great, but because the space forming between us and them expands too rapidly for any signal, spacecraft, or beam of light to ever close the gap. Even a photon moving at sea loses the race. Then the situation became stranger still. In 1998, two independent teams studying distant supernovae discovered that cosmic expansion was not slowing under gravity as expected. It was accelerating. Some unknown phenomenon, now called dark energy, appeared to permeate the universe itself. Current measurements suggest dark energy constitutes approximately 68% of all energy in existence. Saul Perlmutter, Brian Schmidt, and Adam Rice received the 2011 Nobel Prize in Physics for confirming the discovery. The acceleration continues today, quietly, relentlessly. In roughly 150 billion years, every galaxy outside the local group will have crossed beyond the cosmological horizon permanently. Future observers inside the merged remains of the Milky Way and Andromeda will see only darkness beyond their local system. No distant galaxies, no evidence of a larger cosmic web. The wider universe will disappear from observation entirely. Andromeda escapes this fate only because gravity has already tied our galaxies together. Long before expansion can separate us, the two systems will merge into one. But the broader realization changes the meaning of distance itself. The universe is not a stable backdrop waiting to be crossed. It is an expanding architecture of isolation, and the impossibility surrounding Andromeda is only the nearest, gentlest example of a separation quietly increasing everywhere at once. Fold a sheet of paper so that two distant points touch. A pencil pushed straight through the fold crosses the distance instantly, not by traveling across the page, but by leaving the flat geometry entirely. Wormholes emerge from a similar idea, though far stranger in execution. Instead of crossing ordinary distance, they propose a shortcut through spacetime itself. In 1935, Albert Einstein and Nathan Rosen discovered that the equations of general relativity allowed structures later called Einstein-Rosen bridges. These bridges connected separate regions of spacetime through a hidden tunnel. A traveler entering one side could, in principle, emerge somewhere unimaginably distant without traversing the intervening space at all. The mathematics permit this cleanly. That detail matters because wormholes do not technically violate special relativity. Nothing inside the tunnel exceeds light speed locally, the traveler never outruns light through space. Instead, the geometry itself bends so that two distant locations become directly adjacent through higher dimensional curvature. At first glance, the loophole appears perfect, but general relativity introduces a problem immediately. Naturally occurring wormholes collapse almost instantly after forming. The throat of the tunnel pinches shut faster than light itself can cross the structure. A ship approaching the entrance would encounter a disappearing passage before completing the transit. For decades, this ended the discussion. Then, in 1988, physicist Kip Thorne and his collaborators demonstrated that traversable wormholes could remain open mathematically if supported by something called exotic matter. Exotic matter is a hypothetical substance possessing negative mass energy density, meaning it would gravitationally repel rather than attract. Instead of collapsing inward under gravity, the wormhole throat could be forced open by this negative energy. Physics does contain faint hints that negative energy may exist in limited forms. One example is the Casimir effect, a measured quantum phenomenon occurring when two uncharged metal plates are placed extraordinarily close together in a vacuum. Quantum fluctuations between the plates create a tiny pressure imbalance, producing effects mathematically associated with negative energy density. But the scale is microscopic. The distance between the Casimir effect and a traversable wormhole resembles the distance between a candle flame and a supernova. The amount of negative energy required becomes almost incomprehensible. Kip Thorne's own estimates suggested a wormhole large enough for a spacecraft might require negative mass energy comparable to Jupiter converted directly into exotic form. Jupiter contains roughly 1.9 octillion joules of mass energy. No known process produces negative energy remotely approaching this magnitude. And another obstacle waits underneath all of it. Even if a stable wormhole could somehow be created near Earth, one opening would still need to exist at the destination already. A tunnel requires two ends. You cannot place the far end beside Andromeda without first transporting it there through ordinary space. The shortcut solves the travel problem only after the travel problem has already been solved. So the wormhole remains suspended in an unusual category. It is not fantasy. It arises naturally from legitimate equations tested across modern physics. The doorway exists mathematically. The geometry works. But every known attempt to turn the equations into reality collapses under conditions the universe does not appear willing to provide. And yet, wormholes are not the final loophole. Another possibility emerged decades later, stranger even than tunnels through spacetime. In 1994, a young Mexican physicist named Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity, describing a machine that sounded less like physics and more like mythology. The proposal did not attempt to push a spacecraft through space faster than light. Instead, it attempted something stranger. It proposed moving space itself. The idea became known as the Alcubierre drive. Inside the model, a spacecraft rests motionless within a region called a warp bubble. Space ahead of the bubble compresses. Space behind it expands. The ship does not accelerate conventionally, and the passengers inside feel no crushing force. Instead, the bubble carrying them moves across spacetime while the vessel itself remains locally still. That distinction changes everything. Special relativity forbids objects with mass from outrunning light through space. But general relativity allows spacetime itself to expand, contract, and distort without obeying the same restriction. The early universe expanded faster than light during cosmic inflation. Galaxies beyond the cosmological horizon recede faster than light because space stretches between them. Alcubierre realized the equations permitted a spacecraft to exploit that same principle artificially. And remarkably, the mathematics worked. The Alcubierre metric, meaning the specific geometric solution describing the warp bubble, remains a valid solution to Einstein's field equations today. It passed peer review. Physicists continue studying it seriously. The loophole was not fictional. It emerged naturally from the structure of general relativity itself. But the price arrived immediately. The original proposal required exotic matter with negative energy equivalent to the mass energy of Jupiter, the same impossible ingredient demanded by traversable wormholes appeared again at nearly the same scale. Without negative energy, the warp bubble collapsed. Years later, in 2012, Harold White at NASA's Eagle Works laboratory proposed modifying the shape of the warp bubble to reduce the energy requirements dramatically. Instead of Jupiter-scale energies, the revised estimates approached the mass energy equivalent of a large spacecraft, still immense, still dependent on negative energy, but less absurd than before. Then, in 2021, physicist Eric Lentz proposed another variation using only positive energy, eliminating exotic matter entirely. The equations remained mathematically consistent. Yet the required energy still reached hundreds of times Jupiter's total mass converted completely into usable power. The loophole narrowed again. Other problems emerged as researchers examined the geometry more carefully. A warp bubble, once moving, cannot be controlled from inside. The traveler loses causal contact with the outer boundary. Causal contact means the ability for one region to influence another through signals or forces. Inside the bubble, no signal can reach the leading edge to steer, stop, or redirect the motion. The destination must effectively be determined beforehand. Quantum mechanics adds another instability. Hawking radiation, high-energy particles associated with extreme spacetime distortions, would likely accumulate at the bubble's front edge. Calculations suggest the radiation released when the bubble stopped could flood the interior with catastrophic energy. And beneath everything remains the oldest problem of all. To arrange the necessary space-time conditions near Andromeda, you would already need access to Andromeda beforehand. So the Alcubierre drive occupies a peculiar territory in physics. It is not fantasy. The equations are real. The studies are real. Researchers continue refining the mathematics. But every path circles back toward ingredients, energies, and conditions the observable universe does not appear to provide. The two great loopholes now stand examined. Both survive mathematically, both fail physically, and that leaves behind a quieter question, one reaching beyond engineering entirely. Why does the universe permit the idea of escape while withholding the means? A child can outrun a speed limit sign. An aircraft can exceed the sound barrier. Human history is filled with limits that appeared absolute until engineering dissolved them. So it is natural to imagine light speed as another threshold, waiting for a future machine powerful enough to ignore it. But the speed of light is not that kind of limit. It does not behave like a law imposed from outside reality. It behaves more like the scaffolding reality itself is built upon. Physicists shorten the speed of light to a single letter, c. But c is not fundamentally about light. It is the speed of causality, the maximum rate at which any cause can influence any effect anywhere in the universe. It defines how quickly information, force, interaction, and sequence itself can propagate through spacetime. If something exceeded that speed, the consequences would not simply be unusual. They would break the structure, allowing events to exist coherently at all. Imagine sending a faster than light signal from Earth to a distant observer moving relative to you. Under special relativity, different observers disagree about the timing of distant events depending on their motion. At ordinary speeds, this creates no contradiction because causality remains preserved. Causes still precede effects for everyone involved. But faster than light communication changes the geometry completely. For certain observers, the signal would arrive before it was sent. Not metaphorically, literally. A response could then be transmitted backward through another reference frame, creating a closed causal loop where information returns to its own past. Effects begin generating causes. Events occur before the actions producing them. The sequential order underlying physical reality starts collapsing into contradiction. This is why physicists do not describe faster than light travel as merely difficult. It threatens the consistency of time itself. And the remarkable part is how many independent branches of physics converge on the same conclusion. Maxwell's equations describing electromagnetism produce C naturally. Special relativity requires it. General relativity preserves it through spacetime geometry. Quantum field theory, the framework governing subatomic particles and forces, incorporates the same invariant speed into its foundations. Four major theoretical systems, developed independently across different centuries and scales, all arrive at the identical number. That convergence carries enormous weight. Any future theory replacing these frameworks would still need to reproduce C with extraordinary precision because the universe keeps confirming it experimentally. The constancy of light speed has been tested in every direction across enormous energy ranges using atomic clocks, particle accelerators, laser interferometers, and astrophysical observations. So far, no deviation has ever appeared. Current measurements verify its stability to roughly 1 part in 100 quadrillion. The number does not bend. By this point, the shape of the problem changes completely. Andromeda is not unreachable because our civilization remains primitive or temporary. It is unreachable because the universe organizes space, time, energy, and causality in ways that prevent certain distances from ever being crossed meaningfully. The walls are no longer engineering obstacles. They are structural features of existence itself. And once those walls settle into place, the attention shifts naturally away from propulsion and toward the destination waiting beyond them. Because if Andromeda cannot truly be reached, then the galaxy itself begins changing meaning. It becomes less a place to visit and more a distant reality we study entirely through the light it once released toward us. The photons entering your eyes tonight began their journey toward Earth approximately 2.537 million years ago. They departed Andromeda long before modern humans existed, long before language, cities, or recorded memory. During all the time since, those photons crossed intergalactic darkness uninterrupted, carrying with them a frozen image of a galaxy that no longer exists in precisely the form we now observe. This changes the meaning of observation itself. What you see is not Andromeda in the present tense. It is an ancient projection preserved in light. Somewhere inside that galaxy, stars visible in modern telescopes may already be dead. Massive blue stars often survive only a few million years before collapsing into supernovae. Entire planetary systems may have formed after the light departed, cooled, evolved, or vanished again before the image ever reached us. The present-day Andromeda is not hidden behind insufficient technology. It is inaccessible by definition. No information describing its current state has had enough time to arrive here yet. The delay is built directly into spacetime. So, astronomy becomes a kind of archaeology. We excavate the past using light as evidence, reconstructing structures and events from signals already millions of years old by the time they touch our instruments. Every image from Andromeda is effectively a fossil, preserved not in rock but in radiation. This becomes especially clear near the galaxy's center. In 1993, observations from the Hubble Space Telescope revealed that Andromeda possesses an unusual double nucleus structure designated P1 and P2. At first glance, it appeared as though the galaxy contained two central cores orbiting near one another. Further study complicated the picture. P2 is the true center. Buried there lies a supermassive black hole estimated between 100 and 140 million solar masses, roughly 30 times more massive than Sagittarius A star. The black hole occupying the center of the Milky Way. Around this region sits P1, an eccentric disk of older stars displaced slightly from the actual center by complex gravitational motion, still debated decades after discovery. Then astronomers found something stranger still. Inside the central region exists another structure called P3, a compact cluster of hot blue stars orbiting extremely close to the black hole itself. Current models of galactic dynamics struggle to explain how young, massive stars could form and survive in such an extreme gravitational environment. The puzzle remains unresolved. But every detail of this mystery belongs to the ancient Andromeda, not the galaxy existing there now. We do not know whether P3 still maintains the same structure today. The blue stars may have evolved already. Some may have exploded. The black hole at P2 may have consumed additional stars or gas clouds during the intervening millions of years. Entire orbital patterns could have shifted silently while the old light continued traveling toward us. Every photograph from Andromeda is therefore a delayed message from a sender permanently out of sync with its recipient. We receive images of what the galaxy was, never what it is. The separation is no longer merely spatial. It is temporal as well. Even perfect telescopes cannot overcome that. The universe allows us to witness Andromeda only through memories, carried by light. When we picture a galaxy, we imagine the visible parts first: spiral arms, dense star fields, clouds of glowing gas suspended between stars, dust lanes cutting dark paths through luminous regions. But nearly everything we can actually see inside Andromeda represents only a small fraction of what is physically there. Most of the galaxy is invisible. Astronomers call the missing component dark matter. The term does not describe dark material in the ordinary sense. Dark matter does not emit light, absorb light, reflect light, or interact with electromagnetic radiation in any detectable way. Telescopes cannot photograph it directly because, as far as current physics can determine, it remains completely transparent to light itself. Its existence is inferred indirectly through gravity by observing how galaxies behave. The evidence became impossible to ignore during the 1970s through the work of astronomer Vera Rubin. Rubin studied the rotation speeds of spiral galaxies and found something deeply unexpected. According to Newtonian gravity, stars farther from a galactic center should orbit more slowly, just as the outer planets of our solar system move more gradually around the Sun than the inner planets do. Instead, Rubin discovered that the outer stars in galaxies continued orbiting at nearly the same speeds as stars much closer to the center. The visible mass alone could not generate enough gravity to hold those outer stars in place. Something unseen surrounded the galaxies, extending far beyond their luminous disks and contributing enormous additional mass. Without it, the galaxies should have torn themselves apart rotationally billions of years ago. Andromeda possesses one of these structures on an immense scale. Its visible disk stretches roughly 110,000 light years across, yet the surrounding dark matter halo may extend between 1 and 2 million light years outward in every direction. The invisible region vastly exceeds the glowing spiral galaxy embedded within it. At that scale, another realization appears quietly. The dark matter halo surrounding Andromeda already overlaps with the halo surrounding the Milky Way. Long before any stars collide or gas clouds interact, the two galaxies are already touching through these immense gravitational envelopes. They interpenetrate invisibly across intergalactic space, linked by structures no human eye can ever observe directly. The total mass of Andromeda, including its dark matter halo, is estimated between 800 billion and 1.5 trillion solar masses. Approximately 80 to 90% of that mass appears to consist of dark matter rather than ordinary visible material. And still, nobody knows what dark matter actually is. It does not fit into the standard model of particle physics, the framework describing all currently known fundamental particles and forces. Decades of underground detectors, particle collider experiments, cryogenic sensors, and astrophysical surveys have failed to identify it directly. Entire laboratories operate solely to search for interactions that have never conclusively appeared. We can calculate its gravity with remarkable precision. We can map its distribution through galaxies. We can measure its effects across the universe. But we cannot isolate it, classify it, or explain its composition. So the situation becomes stranger again. The galaxy we cannot physically reach is composed mostly of something we cannot even identify. The farther we move into Andromeda's reality, the more the visible universe begins dissolving into structures hidden permanently beyond direct human perception. Across the darkness between galaxies, Andromeda is already moving toward us at roughly 110 kilometers per second. The motion was confirmed in 2012 through precise measurements from the Hubble Space Telescope, which tracked tiny shifts in the galaxy's position against far more distant background objects. The approach is slow on human timescales, almost motionless to perception, yet relentless across cosmic time. The first close passage is expected roughly 4.5 billion years from now. By then, the Sun itself will be nearing the beginning of its red giant phase, gradually swelling as hydrogen fusion in its core declines. Earth's surface conditions may already be unrecognizable long before the galaxies meet, but the merger itself will unfold across hundreds of millions of years, transforming both systems through gravity rather than impact. Because galaxies are mostly empty space, the average separation between stars in the Milky Way is approximately 4 to 5 light years. Even during a galactic merger, the probability of two stars physically colliding remains extraordinarily low. If the Sun were reduced to the size of a grain of sand, the nearest neighboring star would still sit hundreds of kilometers away. A galaxy appears dense only because we observe billions of stars compressed into distant light. So the coming collision behaves less like two solid objects crashing together and more like two weather systems interpenetrating slowly across intergalactic space. Gravitational tidal forces begin the process first. Tidal forces occur when gravity pulls more strongly on one region of an object than another, stretching and distorting the structure over time. During the merger, those forces will pull vast streams of stars outward into enormous luminous arcs, extending millions of light years from the galactic cores. The gas clouds behave differently. Unlike stars, clouds of hydrogen and dust do collide directly. As the two galaxies pass through one another, immense gas reservoirs compress together, triggering violent waves of star formation. Millions of new stars will ignite across the merging structure almost simultaneously, filling the future sky with brilliant young blue, stellar populations burning hotter and shorter than our Sunday. Simulations developed by NASA and Harvard researchers in 2012 suggest the galaxies will not merge immediately after first contact. They will pass through each other, continue outward, slow under mutual gravity, then return again. Several oscillations follow before the systems finally settle into equilibrium. The final merger arrives approximately 6 billion years from now. The result will likely be a giant elliptical galaxy, lacking the graceful spiral structure both galaxies currently possess. Astronomers have informally nicknamed the future system Milkomeda or Milkdromeda, a single gravitational structure formed from two once separate island universes. Our solar system will probably survive the process physically intact. But survival does not mean stability. The Sun may be flung into a different orbital region entirely, perhaps drifting into the outer halo of the merged galaxy, far from the dense central core. And that creates one of the strangest reversals in this story. The galaxy we cannot travel to will eventually arrive here on its own. It will cross the distance not through engineering or acceleration, but through gravity operating patiently across billions of years, indifferent to whether anything inside either galaxy ever wished to meet. Tonight, Andromeda already occupies more space in the sky than most people realize. Its visible width spans roughly 3 degrees, about 6 times wider than the full moon. But the light is diffuse and faint, spread thinly across darkness, so, under modern city skies, the galaxy often disappears completely from unaided vision. That will not always be true. About 1 billion years before the first close encounter, future observers on Earth would notice Andromeda changing slowly across generations. The faint smear would brighten and widen into a distinct glowing oval, visible even through atmospheric haze and artificial light. It would stop looking like an uncertain patch of darkness and begin resembling a permanent celestial structure hanging quietly above the night horizon. 500 million years before collision, details emerge. The spiral arms begin resolving faintly to the naked eye. Dust lanes divide sections of the luminous disk. The galaxy expands across a substantial portion of the sky, no longer a distant object but an enormous visible system suspended beside the Milky Way itself. Human cultures living beneath that sky would grow up with two giant galaxies overhead instead of one. 100 million years before closest approach, the geometry of the heavens starts distorting visibly. Tidal forces reshape both galaxies gradually. The Milky Way's familiar band bends and warps across the sky, while Andromeda's structure stretches outward into elongated arcs. The stable night sky, humanity inherited for millions of years, begins losing its symmetry. Then the galaxies pass through one another. The result would not resemble daylight. The sky would still darken at night, but darkness itself would change character. A deep continuous luminosity would spread across enormous regions overhead. Two galactic cores blaze simultaneously. Vast rivers of stars stretch across the heavens. Triggered star-forming regions ignite where gas clouds collide, filling portions of the sky with dense concentrations of hot young stars. Among the most dramatic structures, would be OB associations, clusters dominated by massive blue stars burning at extremely high temperatures. These stars shine intensely but live briefly, appearing and fading across hundreds of thousands of years as the merger continues reshaping the galaxies around them. Between major passes, tidal streams pulled from both galaxies arc across the sky in luminous bands extending from horizon to horizon. Some streams could span nearly 180 degrees of visible sky, broad enough to divide the heavens into immense flowing structures unlike anything present today. Eventually, after repeated oscillations, the two cores settle into one. During final coalescence, a single brilliant galactic center forms. Depending on Earth's surviving orbital position, that concentrated core may become bright enough to remain faintly visible even during daytime hours. The sky future descendants inherit will bear almost no resemblance to ours. Yet one detail may pass unnoticed by the beings living beneath it. They will not see the Milky Way as a narrow, luminous band crossing the sky because the Milky Way will no longer exist as a distinct spiral structure. They will live inside a merged elliptical galaxy lacking obvious arms, edges, or orientation points. The heavens around them may appear immense but directionless, a smooth ocean of stars without any clear center visible from within. And that may become the strangest transformation of all. Not merely a brighter sky, but the disappearance of the cosmic shape humanity once used to understand where it lived. Long before the Milky Way entered Andromeda's path, other galaxies disappeared into it first. Their stars still remain scattered across Andromeda's outskirts, stretched into enormous currents that drift through its halo like pale scars left by ancient gravitational encounters. These structures are called stellar streams. A stellar stream forms when a smaller galaxy falls into a larger one, and gravity tears it apart gradually over millions of years. The stars do not vanish instantly. They unravel, orbiting outward in elongated ribbons that preserve the memory of the original collision long after the smaller galaxy itself has ceased to exist. One of the largest examples surrounding Andromeda is known simply as the Giant Stellar Stream. The structure extends roughly 120,000 light years from Andromeda's center, a vast arc of displaced stars moving through the galaxy's outer halo. Astronomers identified it as the remnant of a dwarf galaxy consumed approximately 210 million years ago. The original system no longer exists as an independent object. Only its stars remain, redistributed into Andromeda's gravitational structure. But the giant stellar stream was only the beginning. In 2009, astronomers completed the Pan-Andromeda Archaeological Survey, usually shortened to PANDAS, using the Canada, France, Hawaii telescope. The project mapped Andromeda's halo in unprecedented detail and revealed a far more complicated history than previously imagined. At least 13 distinct stellar streams emerged from the data. Additional shell-like overdensities appeared as well, dense regions where stars clustered into curved structures produced by repeated mergers over billions of years. Each stream encoded a separate interaction, preserving the orbital fingerprints of galaxies Andromeda had absorbed across cosmic history. The galaxy approaching us now is therefore not pristine, it is assembled. One of the strangest clues involves M32, a compact elliptical satellite orbiting Andromeda today. M32 appears unusually dense compared to similar galaxies nearby. In 2018, researchers proposed that M32 may actually represent the surviving core of a once much larger spiral galaxy, largely consumed by Andromeda approximately 2 billion years ago. If correct, the implications are immense. Models suggest the destroyed galaxy may once have been the third largest member of the local group, comparable in scale to the Triangulum Galaxy, designated M33. Andromeda did not merely absorb a dwarf system. It may have dismantled an entire major spiral galaxy and left only its compressed central nucleus behind. The chemistry of Andromeda supports this violent history. Astronomers describe chemical richness through metallicity, meaning the proportion of elements heavier than hydrogen and helium contained within stars. Andromeda possesses higher metallicity overall than the Milky Way. Each merger introduced additional generations of enriched stars, gradually increasing the abundance of heavier elements throughout the galaxy. Yet the process has slowed with age. Today, Andromeda forms roughly one solar mass of new stars per year, lower than the Milky Way's estimated range of 1.5 to 3 solar masses annually. The galaxy remains active, but quieter than it once was. Its most aggressive period of growth appears largely complete, and that changes the emotional shape of what is coming toward us. The approaching galaxy is not a young system entering its first collision, it is experienced. It has already absorbed other galaxies repeatedly across billions of years. The Milky Way will not introduce Andromeda to merger. It will simply become the next chapter in a process Andromeda has practiced for most of cosmic history. Around Andromeda, smaller galaxies drift like fragments caught inside a larger gravitational tide. Some are dense and ancient, others are diffuse and unstable. Together, they form a retinue of at least 30 confirmed satellite galaxies orbiting the larger system, a more extensive galactic family than the one surrounding the Milky Way. Each companion carries its own history. Some also carry scars. Among the closest and strangest is M32, a compact elliptical galaxy compressed into an unusually dense concentration of stars. Modern observations suggest it was not always this small. Evidence now points toward M32 being the stripped core of a once much larger spiral galaxy whose outer structure was gradually torn away by Andromeda's gravity across billions of years. What remains is one of the densest stellar environments known outside globular clusters. Nearby drifts M110. Unlike M32, M110 appears soft and diffuse, a dwarf elliptical galaxy composed almost entirely of old stars. Little active star formation occurs there now. The galaxy glows faintly with ancient stellar populations that formed long ago and have since aged quietly in orbit around Andromeda's larger mass. Beyond those major companions lies an expanding catalog of smaller satellites discovered mostly within the last 2 decades through deep imaging surveys. Some are dwarf spheroidals, meaning faint rounded galaxies containing little gas or ongoing star formation. Others are dwarf irregulars, chaotic systems lacking organized structure. Many are so dim that astronomers overlooked them entirely until modern digital surveys revealed their presence against the background sky. But one discovery complicated the picture further. Data from the Pan-Andromeda Archaeological Survey showed that several satellites appear arranged along a common geometric plane rather than orbiting randomly in three-dimensional space. This structure, called a planar alignment, remains controversial because standard dark matter cosmological models generally predict a more scattered distribution. Theories continue attempting to explain why so many satellites occupy such a thin shared arrangement around Andromeda. Some companions are already dissolving. Andromeda 27, one of the more recently confirmed large satellites, shows clear evidence of tidal disruption. Its stars are being stretched outward by gravitational forces, as the galaxy slowly comes apart. Over enough time, it may cease existing as a distinct object entirely, its stars absorbed into Andromeda's broader halo. Then there is M33, the Triangulum Galaxy, located approximately 2.73 million light years from Earth. M33 may orbit Andromeda on a wide, loosely bound trajectory. It stands as the third major galaxy of the local group and contains roughly 40 billion stars. Under exceptionally dark skies, it becomes the farthest object visible to the naked human eye, though most people never notice the faint blur suspended at the edge of perception. Simulations suggest M33 may eventually participate in the coming merger as well. In some models, it collides with the Milky Way before Andromeda arrives. In others, it becomes absorbed later into the combined galactic system. So Andromeda's companions are more than neighboring objects. They form a living archive. Each orbit, distortion, and stellar stream records an earlier interaction preserved across cosmic time, the way rings preserve the history of a tree long after each season has passed. If we step far enough outward, the Milky Way and Andromeda stop feeling unique. They become the two largest structures inside a much broader gravitational neighborhood called the local group, a collection of approximately 54 galaxies spread across roughly 10 million light years of space. Most of those galaxies are small. Beyond the Milky Way, Andromeda, and the Triangulum Galaxy, nearly every remaining member of the local group belongs to the dwarf category, dim systems containing relatively few stars compared to the giant spirals dominating the region. Some orbit quietly for billions of years. Others are slowly being dismantled by tidal gravity from larger neighbors. Our own nearest companions are already visible from Earth's southern hemisphere. The large and small Magellanic Clouds orbit the Milky Way at distances of approximately 160,000 and 200,000 light years, respectively. To the naked eye, they appear as detached cloudy patches separated from the main galactic band, faint neighboring systems suspended in darkness beside our own. But even these nearby galaxies are not stable. Stretching behind them is the Magellanic Stream, an enormous ribbon of hydrogen gas extending roughly 150 degrees across the sky. The stream formed because the Milky Way's gravity is actively pulling material from both satellite galaxies, stripping gas away gradually as they orbit through our galactic halo. Gravity scales upward seamlessly from there. The local group itself belongs to a much larger structure called the Virgo supercluster, an immense collection of galaxy groups spanning approximately 110 million light years. For decades, astronomers treated the Virgo supercluster as one of the largest known cosmic structures. Then the frame widened again. In 2014, astronomer Brent Tully and collaborators mapped galaxy motions across even greater distances and identified a larger structure encompassing Virgo itself. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea contains roughly 100,000 galaxies distributed across approximately 520 million light years of space. The Milky Way occupies only a peripheral region inside it. We exist near the outer edge of this supercluster, within a comparatively low-density environment far from its gravitational center. That center is associated with a mysterious region known as the Great Attractor, an enormous concentration of mass located roughly 250 million light-years away. Everything around us is slowly falling toward it. The Milky Way, Andromeda, the local group, and the surrounding galaxies all drift through space at approximately 600 kilometers per second in the direction of this unseen gravitational source. We do not feel the motion because everything near us moves together within the same large-scale flow, and there is no mechanism capable of stopping it. At every level, the universe repeats the same architecture. Galaxies gather into groups, groups gather into superclusters, superclusters stretch into larger cosmic structures separated by expanding voids too immense to cross. Each region becomes its own gravitational island, isolated from the others across time. Seen this way, Andromeda's unreachability stops being unusual. It becomes local evidence of a deeper cosmic pattern. Everywhere we look, matter gathers into separated archipelagos, suspended inside an expanding universe, each island carrying its own stars, history, and darkness beyond the reach of the next. On December 25th, 2021, a telescope unfolded in deep space, approximately 1.5 million kilometers from Earth. Suspended near the Sun-Earth L2 point, protected by a multi-layer shield thinner than paper, the James Webb Space Telescope began observing the universe primarily through infrared light, wavelengths longer than visible light, and largely invisible to human eyes. That difference matters enormously for Andromeda. Dust blocks visible light efficiently. Dense lanes of interstellar dust scatter and absorb optical wavelengths, concealing large portions of galactic interiors from ordinary telescopes. Infrared light behaves differently. It passes through dust far more effectively, allowing Webb to peer into regions previous instruments could only partially resolve. Andromeda immediately became more complicated. Webb's imaging of star-forming regions revealed intricate bubble and shell structures, sculpted by stellar winds from massive stars. Stellar winds are streams of charged particles continuously expelled from hot stars at tremendous speeds, pushing surrounding gas outward into expanding cavities. Similar structures exist inside the Milky Way, but Andromeda's patterns appeared denser, more layered, and more numerous than models based on our own galaxy had predicted. The telescope also changed the scale of observation itself. Previous studies often treated Andromeda statistically, estimating stellar populations by measuring combined light from crowded regions. Webb can resolve many individual stars directly inside Andromeda's disk. That transforms galactic analysis from approximation into census work, allowing astronomers to map stellar ages and distributions star by star across portions of another galaxy. But clarity produced new contradictions. Webb's stellar census showed that older stellar populations near Andromeda's inner regions do not align cleanly with existing merger models. The arrangement suggests disturbances more complex than previously reconstructed from visible observations alone. Something altered the galaxy's architecture in ways astronomers still cannot fully explain from current simulations. Near the center, the mystery deepens further. The P3 cluster, those hot blue stars orbiting close to Andromeda's central black hole, has been examined in greater detail through Webb's infrared sensitivity. Their orbital properties are now measured more precisely than before, yet the core problem remains unresolved. Current theories still struggle to explain how young massive stars could form and persist so near an environment dominated by intense tidal gravity. The double nucleus itself also appears stranger under closer examination. Webb observations of P1 and P2 revealed additional complexity inside the eccentric stellar disk surrounding the black hole region. Stellar motions suggest internal dynamics not fully captured in earlier models. The structure behaves less like a settled configuration and more like an active gravitational system still preserving evidence of older interactions. And that may be the telescope's most important contribution. Each increase in observational power was once expected to simplify Andromeda by replacing uncertainty with precision. Instead, the opposite keeps happening. The clearer the galaxy becomes, the more layered its history appears. Questions multiply faster than answers. So the James Webb Space Telescope does not function as a vehicle carrying humanity closer to Andromeda. It remains exactly where we are, separated by the same impossible distance. But it sharpens the fossil light arriving from that galaxy, revealing more detail inside the ancient signal. The telescope cannot close the gap between galaxies. It can only illuminate more of the past suspended within it. Inside Andromeda, roughly 1 trillion stars burn across its spiral structure, 2 to 3 times more than the Milky Way contains. Most are small dim stars, invisible individually from Earth, scattered through dust lanes, stellar clusters, and quiet outer regions we can barely resolve, even with our most powerful instruments. Some of those stars resemble our Sunday. Astronomers classify stars by temperature and color. G-type stars, like the Sun, burn steadily for billions of years and are considered promising hosts for habitable worlds. K-type stars are slightly cooler and smaller, but often survive even longer, providing stable environments over immense timescales. Both types exist throughout Andromeda in enormous numbers, and recent discoveries have changed how we think about planets themselves. The Kepler and TESS space missions revealed that planetary systems are not rare exceptions inside galaxies. They appear almost everywhere. Most stars in the Milky Way likely host at least one planet, and rocky planets inside habitable zones, regions where temperatures may allow liquid water, occur around a substantial fraction of Sun-like stars. Applying those statistics to Andromeda produces staggering numbers. Hundreds of billions of planets may orbit stars there. Potentially billions could exist within habitable temperature ranges. Even conservative estimates imply worlds beyond counting, spread across the galaxy's disk and halo. Andromeda also possesses a temporal advantage. The galaxy is approximately 10 billion years old, older than the Milky Way by more than 1 billion years. On Earth, complex technological intelligence required roughly 4 billion years to emerge after the planet formed. Some regions of Andromeda have existed long enough for that process to occur multiple times over. Civilizations there, if they exist or once existed, may have begun long before Earth formed its first multicellular organisms. This leads naturally into the Fermi paradox, the contradiction between the apparent probability of advanced civilizations and the complete absence of confirmed evidence for them. Theoretical studies suggest that even without faster-than-light travel, a civilization only modestly more advanced than ours could spread through an entire galaxy using self-replicating probes moving at sublight speeds. The process would take millions of years, but Andromeda has had billions available. So where are the signs? Astronomers have searched for possible technosignatures, detectable evidence of advanced engineering. One hypothetical example is a Dyson sphere, a massive structure surrounding a star to capture much of its energy output. Others include unnatural radio transmissions or unusual stellar dimming patterns inconsistent with natural astrophysical processes. No confirmed evidence has appeared, but the situation is stranger than simple absence. The light reaching Earth from Andromeda tonight departed 2.537 million years ago. Any civilization we observe there belongs to that ancient era, not the present day. A civilization that collapsed 1 million years ago would still appear active in the light currently crossing intergalactic space toward us. Likewise, a civilization that emerged yesterday by Andromeda's clocks remains completely invisible from Earth because its light has not yet arrived. So the search for life in Andromeda is not occurring in real time. We are examining an ancient archive preserved in radiation, searching for traces of intelligence that may already be extinct, transformed, or unrecognizable by now. The question, therefore, becomes temporally displaced. Any answer exists somewhere inside the distant past, sealed behind millions of years of light travel we cannot shorten, bypass, or overcome. Suppose we abandon the idea of travel completely. No ships, no engines, no attempt to cross the distance physically. Could we at least speak across it? The answer still runs into the same wall. Every known form of communication available to physics belongs to the electromagnetic spectrum. Radio waves, visible light, microwaves, X rays, laser pulses, radar transmissions, all are electromagnetic waves moving through space at exactly the speed of light, the same universal constant governing everything discussed so far. Nothing carrying information travels faster. A signal transmitted from Earth toward Andromeda today would require approximately 2.537 million years to arrive. If a civilization there detected the message immediately and responded without delay, the return transmission would need another 2.537 million years to cross back. The shortest possible conversation between our galaxies therefore lasts over 5 million years. And humanity has not even begun crossing that gap. The oldest radio signals ever produced by Earth originated only a little more than 1 century ago. Those broadcasts, along with television transmissions and radar pulses, now form an expanding sphere moving outward through the Milky Way at light speed. Its radius measures roughly 100 to 120 light years. That sounds large until Andromeda enters the calculation. Our farthest signals remain approximately 2.437 million light years short of reaching the neighboring galaxy. Even if every transmitter on Earth broadcast continuously at maximum power beginning tonight, the first detectable human signal would not arrive in Andromeda until the year 2,539,026. By then, every civilization currently existing on Earth will be gone. But reverse the perspective for a moment. If astronomers in Andromeda aimed telescopes toward the Milky Way tonight, they would not see cities, satellites, or evidence of intelligent technology. The light reaching them departed our galaxy 2.537 million years ago, before Homo sapiens existed, before agriculture, before language, before organized fire. The most advanced hominids alive on Earth at that moment were still shaping primitive stone tools. To observers there, humanity does not yet exist. Not because we are hiding, and not because our signals failed. We simply had not emerged meaningfully when the light now reaching Andromeda began its journey outward. This changes the nature of isolation itself. The separation between galaxies is not merely physical distance measured in kilometers or light years. It is communicative isolation, epistemic isolation, epistemic meaning related to knowledge itself, what can be known, exchanged, or shared between distant observers. We cannot meaningfully converse with Andromeda because no exchange can occur on timescales compatible with biological memory, civilization, or continuity. Even a perfectly functioning communication system collapses under the burden of time. A genuine dialogue between galaxies would require a civilization capable of preserving language, purpose, records, and identity across millions of years without interruption. It would demand patience beyond anything human history has ever demonstrated. And even then, every sentence exchanged would belong mostly to the dead by the time the answer arrived. We have never crossed the gulf between galaxies. No probe has entered Andromeda. No human instrument has approached even a tiny fraction of the distance separating us from it. And yet we can describe its structure, estimate its age, map its halo, weigh its black hole, and reconstruct parts of its history with astonishing precision. All from here. The distance to Andromeda is now known to within roughly 1% uncertainty. We know its visible disk spans about 220,000 light years. We know its stellar population contains approximately 1 trillion stars. We know the approximate distribution of its dark matter, the rate at which it forms new stars, the chemical richness of its gas, the motions of its satellites, and the scars left by ancient mergers. None of this required movement toward the galaxy itself. The knowledge came through light. Spectroscopy made much of it possible. Spectroscopy means separating light into its component wavelengths, like a prism creating a rainbow, then reading the patterns embedded inside. Different elements absorb and emit specific wavelengths. Hydrogen leaves one signature, helium another, iron another still. From those patterns, we determine composition, temperature, density, and velocity. A galaxy becomes readable. Cepheid variable stars provided distance. These stars brighten and dim at predictable rates, directly tied to their true luminosity. By comparing true brightness with apparent brightness, astronomers calculate distance across millions of light years with remarkable precision. Gravitational lensing revealed hidden mass. Proper motion studies tracked tiny positional changes over decades. Infrared astronomy pierced dust clouds opaque to visible light. Each method translated ancient photons into information. The telescope, therefore, functions as something stranger than a machine for seeing far away. It is a translator. It converts light that has traveled for millions of years into measurable knowledge about places no living thing can visit. The photons arriving tonight carry encoded records of temperatures, motions, chemical histories, magnetic fields, and stellar deaths from a galaxy permanently beyond direct human reach. This creates a remarkable historical reversal. 15th century European sailors knew less about continents on Earth than modern astronomers know about Andromeda. Those continents could be reached within weeks by wooden ships and favorable winds, yet vast regions remained blank on their maps. Andromeda cannot be reached at all, but there are limits the telescope cannot overcome. We cannot observe Andromeda as it exists now, only as it existed 2.537 million years ago. We cannot determine whether a planet there currently hosts life. We cannot stand beneath one of its skies and look outward from inside the galaxy itself. We cannot know what its central black hole is consuming at this exact moment. These are not unsolved questions awaiting better instruments. They belong to a different category entirely. An unsolved question assumes an answer remains accessible with enough time, intelligence, or technology. But physics creates another class of question, one permanently sealed by the finite speed of causality itself. Andromeda contains many such questions. The boundary separating us from that galaxy is therefore not only spatial, it is epistemological, a limit defining what can ever be known by beings confined within the structure of this universe. Long before cities, before writing, before memory itself, the light now entering your eyes began its journey from Andromeda. It departed into intergalactic darkness while Earth was still becoming recognizably human. 2.537 million years ago, the Pliocene epoch was ending. The Pleistocene had just begun. Ice sheets slowly expanded across parts of the northern hemisphere in repeating climatic pulses that would shape the future of every species on Earth. The world was colder then. Grasslands spread across Africa. Ancient horses wandered North America. Saber-toothed cats hunted in open plains. Giant ground sloths moved through South American forests. Entire ecosystems existed that no human being would ever witness, and humanity itself barely existed at all. Homo habilis had only recently appeared. These early hominids stood upright, carried crude stone tools, and possessed brains roughly half the volume of modern humans. Their tools were simple, fractured rocks, shaped enough to cut flesh or crack bone. Nothing more. Anatomically modern Homo sapiens would not emerge for another 2.3 million years. No language had formed in the modern sense, no myths, no astronomy, no mathematics, no cities glowing beneath night skies. Controlled fire had likely not yet appeared. The oldest strong evidence for habitual fire use dates to roughly 1 million years ago, far later than the departure of the light, now reaching Earth from Andromeda. Burial rituals had not begun. Art did not exist. Religion did not exist. History did not exist. The most cognitively advanced thing on Earth was a hominid striking stones together beside migrating animals beneath unfamiliar constellations. And yet the photons arriving tonight were already traveling during those 2.537 million years. Every chapter of human existence unfolded. Agriculture emerged. Empires rose and collapsed. Languages formed and vanished. Religions spread across continents. Entire libraries burned. Telescopes were invented. Spacecraft left Earth. Human beings split the atom, mapped genomes, photographed black holes, and measured the expansion of the universe, all while Andromeda's light continued crossing the dark. The galaxy itself changed during that passage. Massive O-type stars, the hottest and shortest lived stars known, survive only 1 to 10 million years before exploding as supernovae. Since Andromeda's light departed, entire generations of such stars have been born and destroyed multiple times. Planetary systems may have formed from the remnants. Others may have frozen into silence. Some stars visible in Andromeda tonight no longer exist. From inside the galaxy, its constellations have shifted. Orbital motions altered the arrangement of stars. Nebulae expanded. Black holes consumed matter. Stellar clusters drifted through gravitational tides, invisible across intergalactic distance. But we cannot see any of it yet. What arrives tonight is a surviving fragment of an ancient moment, preserved only because light travels at a finite speed through spacetime. You are not witnessing Andromeda in the present tense. You are intercepting a message released before human civilization, before human memory, before humanity itself had properly begun. This is what it means to look across millions of light years. For most of human history, the universe appeared stable. The stars moved across the sky with dependable rhythms. Galaxies seemed fixed in place. Distance felt permanent, like architecture. But the architecture is moving. The expansion discovered by Edwin Hubble was not a brief event from the distant past. Space continues stretching now, at this moment, everywhere simultaneously. More unsettling still, observations gathered over the last several decades show the expansion is accelerating. It is speeding up. The original evidence came from distant supernova surveys in 1998. But later measurements confirmed the same conclusion through independent methods, including baryon acoustic oscillations, gravitational lensing studies, and precise observations of the cosmic microwave background. Something is pushing the universe apart faster over time. That something is called dark energy. We still do not know what it is. The consequence reaches far beyond astronomy. The cosmological horizon, the distance beyond which space expands faster than light can cross it, is not stationary. As expansion accelerates, more galaxies gradually slip beyond that boundary. Their light becomes increasingly red-shifted, stretched into longer wavelengths until it fades beyond detectability entirely. The galaxies do not vanish suddenly. They dim slowly. Their recession speeds increase. Their ancient light thins across expanding space until eventually no future observer can detect them at all. In approximately 150 billion years, every galaxy outside the local group will have crossed permanently beyond the cosmological horizon. No signal sent from Milkomeda, the merged descendant of the Milky Way and Andromeda, will ever reach them again. They will be causally disconnected forever. Future civilizations living inside Milkomeda may become extraordinarily advanced. They may master physics beyond anything known today. But when they look outward, they will see only darkness surrounding a single isolated galaxy. Nothing else. The evidence for cosmic expansion will be gone. The cosmic microwave background radiation, the afterglow of the Big Bang itself, will have red-shifted into wavelengths so enormous that no practical detector could observe it. The Hubble constant will become immeasurable because there will be no external galaxies left whose recession velocities can be compared against distance. From their perspective, the universe may appear eternal and static. They may never discover the Big Bang at all. This gives our era an unusual position in cosmic history. We live during what cosmologists call the stelliferous era, the age when stars actively burn and galaxies remain visible across immense distances. But more specifically, we live during the narrow interval when the structure and origin of the universe are still observable. The window is temporary. The measurements being made now of Andromeda's motion, of large-scale galaxy distributions, of primordial microwave radiation left from the early universe, may become impossible for any civilization born later in cosmic time. The universe is therefore not merely expanding away from us physically, it is gradually erasing the evidence of its own past. And the unreachable glow of Andromeda, hanging tonight beyond all possibility of travel, is one of the closest visible signs that the isolation has already begun. Science is often described as a process of illumination. A question begins in darkness, then gradually moves toward explanation through observation, experiment, and measurement. Across centuries, mysteries become facts, unknowns become knowns. But Andromeda reveals a different category entirely. Some questions do not remain unanswered because our instruments are weak or our theories incomplete. They remain unanswered because the structure of spacetime itself prevents answers from ever arriving. The first unknowable is the simplest. We cannot know Andromeda's current state. Every image, every spectrum, every observation records only the galaxy as it existed 2.537 million years ago. Even a perfect telescope cannot bypass the finite speed of light. The present tense is inaccessible. Whether any planet in Andromeda currently hosts life belongs to the same category. We may estimate probabilities using planetary statistics from the Milky Way. We may model habitable zones and stellar lifetimes. But no signal, probe, or observation can reveal what is happening there now on any meaningful timescale. The answer may already exist. We simply cannot reach it. There is also a perspective forever denied to us. No instrument can show what the local group looks like from the surface of a world inside Andromeda. We can simulate the geometry. We can calculate probable star distributions. But simulation is not observation. No human eye will ever confirm the view. The uncertainty extends inward toward Andromeda's center. Its supermassive black hole may currently be dormant, or it may be consuming gas clouds, generating intense radiation and relativistic jets invisible to us because the evidence has not yet crossed intergalactic space. We do not know what it is doing tonight. The same applies to the P3 cluster, the compact group of hot blue stars orbiting near the galactic core. Those stars may still exist in their observed configuration. Gravitational interactions may have scattered them long ago. Some may already have exploded as supernovae. Their fate is hidden behind time itself. Even seemingly countable things remain unreachable. We cannot determine the actual number of planets in Andromeda. We extrapolate from observed planetary frequencies in the Milky Way and derive estimates reaching into the hundreds of billions. But no survey can individually confirm them across 1 trillion stars. The satellite galaxies surrounding Andromeda contain further unknowables. Some may already have been torn apart by tidal forces since the light we see departed. Others may have merged completely into the larger galaxy. Their current structures are inaccessible to observation. There are unknowable skies as well. What does the night sky look like from a planet orbiting in Andromeda's outer halo, looking back toward the Milky Way and Triangulum galaxy? We can calculate approximate brightness and geometry, but no calculation can verify itself through direct experience. And perhaps most hauntingly, there may already be signals crossing the void between galaxies, natural emissions, artificial transmissions, silent carriers of information moving for millions of years through darkness. Whether anything will ever receive, decode, or understand them may itself be unknowable. This is the distinction Andromeda forces upon us. Unknowns are temporary, unknowables are structural. The universe contains both. The human mind did not evolve for galaxies. It evolved for weather patterns, nearby predators, familiar landscapes, and social groups small enough to remember individually. Our ancestors navigated distances measured in walking days. They tracked seasons, rivers, coastlines, and migrating animals. Even the horizon itself remained reachable. But Andromeda exists beyond every instinct the brain was designed to handle. 2.537 million light years can be written, calculated, visualized in diagrams, even converted into kilometers. Yet the number never fully becomes real inside the nervous system. You can understand it intellectually while remaining emotionally untouched by its scale. The mind has no sensory framework for it. A mile walked produces exhaustion. A mountain produces perspective. An ocean crossing produces duration. These experiences anchor scale to the body itself. But intergalactic distance exceeds bodily intuition so completely that it remains abstract no matter how precisely described. Astronauts have reported something related, though smaller in scale. Psychologists call it the overview effect, a cognitive shift experienced when seeing Earth directly from orbit. From space, national borders vanish, atmospheric fragility becomes visible. The planet appears isolated and finite against blackness. The effect emerges not from information but from perception. The eyes confirm what the intellect previously struggled to hold. Many astronauts describe the experience as permanently transformative. Some become more environmentally conscious. Others report intensified feelings of unity or existential vulnerability. The reaction occurs because the brain finally encounters scale directly through sensory experience rather than through explanation alone. But there can be no Andromeda equivalent. No human being will ever occupy a vantage point where Earth and Andromeda are simultaneously visible to unaided senses in any meaningful way. There is no overlook above the local group, no physical perspective from which intergalactic structure becomes intuitively graspable. We remain trapped inside abstraction. Carl Sagan understood this tension when he reflected on the pale blue dot photograph in 1990. Voyager 1 captured Earth from roughly 6 billion kilometers away, near the edge of the solar system. In the image, Earth appears smaller than a pixel suspended inside scattered sunlight. That photograph changed people. It produced a genuine cultural reckoning with scale and fragility because the image transformed astronomical knowledge into sensory evidence. You could finally see human smallness directly. But Andromeda lies roughly 422,000 times farther away than Voyager's position during the pale blue dot image. No spacecraft will ever photograph Earth from there. No human civilization will wait long enough. The isolation, therefore, exists in a peculiar psychological state. We know it without experiencing it. Researchers studying awe often describe the emotion as requiring perceptual vastness, an encounter with something physically immense that forces the mind to reorganize itself. Towering mountains, storms, cathedrals, eclipses, and deep star fields can all produce it. Andromeda resists even that. Its true scale remains permanently beyond perception, accessible only through mathematics, instruments, and inference. Our relationship with it is mediated entirely through thought. But thought itself is extraordinary. A species that evolved on an ordinary planet around an ordinary star somehow learned to calculate the distance to another galaxy, reconstruct its history, measure its motion, and understand why it cannot be reached. The inability to feel the scale completely does not diminish the achievement of comprehending it at all. The same laws that isolate Andromeda from us also preserve it. For all the distances, delays, and impossibilities described so far, there is another side to the separation. The galaxy remains almost perfectly stable within human experience precisely because it is so far away. Nothing we do reaches it quickly enough to matter. The light arriving tonight left Andromeda 2.537 million years ago. Tomorrow night, slightly newer light arrives. The difference between those two images is separated by only 24 hours across a journey spanning millions of years. To human perception, the galaxy does not move at all. Its position changes so slowly that entire civilizations pass beneath it without noticing any alteration. Empires rise and collapse, languages emerge and vanish, religions spread, borders shift. Technologies transform daily life beyond recognition. Andromeda remains. Homo habilis likely saw the same faint smear suspended in the night sky, though without language to describe what it was. The first Homo sapiens inherited it unchanged. Ancient Persian astronomers recorded the same dim cloud. Sailors crossed oceans beneath it. Edwin Hubble studied it through glass photographic plates in 1923. Tonight, it appears essentially identical, and long after our own moment passes, it will continue appearing the same to whatever intelligence follows us. The constancy comes directly from the same finite speed of light that prevents contact. Distance slows visible change until permanence emerges. The unreachable becomes enduring. There is a particular calm hidden inside that realization. Human life unfolds through instability. Bodies age, buildings decay, Memories distort, political systems fracture. Even landscapes shift over time through erosion, climate, and catastrophe. But Andromeda exists outside those rhythms, not because it is eternal, but because its changes occur too slowly and too far away for human timescales to register them. The galaxy becomes a fixed point against which temporary things reveal themselves as temporary. Its indifference carries a strange softness. Andromeda will appear tonight, whether human concerns succeed or fail, not coldly, not cruelly, more like the ocean continuing its tides, regardless of individual lives spent beside it. Permanence rarely notices the temporary because permanence operates on different scales entirely. But the separation offers another kind of reassurance as well. The barriers face both directions. The same physics preventing us from reaching Andromeda also prevents anything in Andromeda from easily reaching us. The speed of causality protects as much as it confines. Intergalactic distance forms a buffer so vast that even hypothetical civilizations, millions of years older than ours, remain trapped behind the same structure of spacetime. Isolation becomes mutual. In that sense, the scale of the universe is not merely a source of insignificance. It is also the reason the night sky remains stable enough for culture, navigation, mythology, and memory to form around it. If galaxies shifted visibly each year, if stars rearranged themselves nightly, the sky would never become familiar. But it does become familiar. The stars return to nearly the same positions every evening because the cosmos is unimaginably large. The ceiling above humanity tonight is effectively the same ceiling that watched the first fires burn, the first cities rise, and the first astronomers look upward, asking what waited beyond reach. Long before human beings understood galaxies, the atoms composing our bodies were already traveling. Carbon formed inside ancient stars through nuclear fusion, the process where lighter atomic nuclei combine under immense pressure and temperature to create heavier elements. Oxygen emerged the same way. So did calcium in bone, iron in blood, and phosphorus in every cell carrying genetic information through your body tonight. Those stars died violently. Supernovae scattered their material outward across interstellar space, enriching cold clouds of gas and dust with heavier elements unavailable during the universe's earliest years. New stars condensed from those enriched clouds. Around some of them, planets formed. Eventually, on one small world orbiting one ordinary star, chemistry became biology, and biology became awareness. The same physical sequence unfolded inside Andromeda. Its stars forged the same elements through the same reactions, governed by the same constants of physics. The carbon within a hypothetical living organism there would be indistinguishable from the carbon moving through your bloodstream now. At the deepest level, we and Andromeda are not fundamentally separate things. We are different arrangements of matter produced by the same cosmic engine operating in different regions of space across billions of years. Distance divides us physically, but origin connects us completely. But something unusual happened here. Across 13.8 billion years of cosmic evolution, gravity assembled galaxies, stars ignited, planets cooled, molecules organized, and eventually nervous systems emerged capable of abstraction. Through that chain of events, the universe produced a configuration of atoms able to calculate the distance between galaxies it cannot reach. That outcome was never guaranteed. Physics permits consciousness, but does not require it. Most of the universe unfolds without observation. Stars burn for millions or billions of years without witnesses. Black holes merge in total darkness. Entire galaxies rotate silently beyond every horizon capable of seeing them. And yet, here we are, not outside the cosmos observing it from safety, but inside it, produced by it, carrying within fragile biological structures an understanding of realities vastly larger than ourselves. We derived the Lorentz factor. We measured the expansion of space. We identified the limits imposed by causality itself. We learned why Andromeda cannot be reached. There is something quietly extraordinary in that fact. The universe generated from ordinary matter obeying ordinary physical laws, organisms capable of discovering the rules governing their own confinement. And perhaps stranger still, those rules exist whether anyone understands them or not. The distance between galaxies is real, independent of observers. The speed of light remains constant without measurement. Physics does not need witnesses to function, but relationships require minds to recognize them. The Milky Way does not know how far away Andromeda is. Andromeda does not know it is approaching the Milky Way. Galaxies possess no awareness of the structures they inhabit or the histories they carry. We do. Inside human thought exists information about the universe that the universe alone does not explicitly contain. A distance becomes meaningful only when something can measure it. Isolation becomes tragic, beautiful, or profound only when something can understand what isolation means. We are not separate from the cosmos, looking inward from outside the frame. We are one consequence of the cosmos becoming aware enough to discover the architecture surrounding it, including the boundaries it cannot cross. There is a timescale on which galaxies themselves become temporary. In approximately 4.5 billion years, Andromeda and the Milky Way begin their final approach. Over the following billions of years, both spiral structures unravel under gravity. Their stars scatter into long tidal streams. Gas clouds collide and ignite new waves of star formation. Eventually, the two systems settle into one vast elliptical galaxy, informally called Milkomeda. By then, the Sun will be nearing the end of its stable life. But even Milkomeda is not permanent. Stars exist because gravity compresses hydrogen until nuclear fusion begins, converting mass into light across immense stretches of time. Yet stars are finite machines. Each one exhausts its fuel eventually. Massive blue stars die quickly. Smaller red dwarfs endure longer, sometimes for trillions of years. Even they will fade. In approximately 100 trillion years, the stelliferous era ends. That is the epoch we currently inhabit, the era when stars shine and galaxies remain illuminated against the dark. After the final stars extinguish themselves, the universe enters a colder age, populated mostly by stellar remnants, white dwarfs, neutron stars, and black holes drifting through expanding emptiness. Light becomes rare. Temperature differences disappear slowly. Matter spreads thinner. The cosmos grows quieter than anything living today could meaningfully imagine. But black holes remain. A black hole is a region where gravity becomes so intense that escape velocity exceeds the speed of light itself. For decades, they were considered eternal. Then, in 1974, Stephen Hawking demonstrated through quantum mechanics that black holes should emit faint thermal radiation and gradually evaporate. Hawking radiation changes everything. Even black holes die eventually, although the timescales are almost incomprehensibly long. The largest may survive for approximately 10 to the power of 100 years, a number so enormous that written human history occupies less than an invisible fraction of it. And after that comes heat death. Entropy, the tendency of energy to spread into equilibrium, reaches its maximum state. No usable energy gradients remain, no stars burn, no structure changes meaningfully. Information processing becomes impossible because no work can be extracted from anything anywhere. Against that backdrop, the distance to Andromeda becomes strangely local. Our inability to cross 2.537 million light years belongs to an extraordinarily early civilization living near the beginning of cosmic history. We exist during the brief luminous interval when galaxies still shine, when the cosmic microwave background remains detectable, when the large scale architecture of the universe can still be observed directly. And within that narrow interval, something unusual occurred. A species emerged capable of measuring the separation between galaxies, mapping invisible dark matter halos, calculating relativistic energy requirements, identifying black holes, and understanding precisely why the journey could never happen. That achievement remains remarkable, regardless of the outcome. Most of the universe contains no observers at all. Stars burn unattended. Black holes consume matter without record. Dark matter halos pass silently through one another across millions of light years. Only here, in one small region surrounding one ordinary star, did matter organize itself into forms capable of asking what any of it means. What remains, when travel is impossible and communication fails across cosmic distance, is the act of understanding itself. The impossibility does not diminish that understanding. It sharpens it, defining its edges with extraordinary precision. Somewhere above the turning Earth tonight, beyond the atmosphere's thin veil of moving air, a stream of photons is still arriving. If the sky above you is dark enough, and if distant city lights do not drown the horizon in artificial glow, you can lift your eyes toward the constellation of Andromeda and see a faint, elongated blur suspended between the stars. No telescope is required, no observatory. Human eyesight alone is enough. That small smear of light appears fragile, but it survived a journey almost beyond comprehension. The photons entering your eyes tonight departed Andromeda 2.537 million years ago, when Earth belonged to a different world entirely. Ice ages had only begun their long advance across the northern hemisphere. The earliest members of the genus Homo moved through African grasslands carrying crude stone tools shaped by unsteady hands. No cities existed, no written language, no memory preserved beyond living minds. The light was already traveling then. It crossed the sparse intergalactic medium, the thin distribution of atoms scattered between galaxies, so diffuse that entire cubic meters contain only single particles drifting in darkness. It moved through magnetic fields, past wandering gas clouds, and across the invisible overlap where the dark matter halos of Andromeda and the Milky Way already interpenetrate silently across enormous distances. Nothing guided it. The photons were not sent toward Earth with intention or message. They carried no awareness of destination. Light does only one thing. It moves through space-time at the fixed speed permitted by the structure of the universe itself, continuing uninterrupted until something absorbs it. Tonight, perhaps, that something is you. A particle of light leaving another galaxy before human civilization existed may end its journey inside the cells of your retina during one ordinary evening on Earth. For an instant, your nervous system completes a path stretching across millions of years and millions of light years simultaneously. And that connection is real. We cannot cross the distance physically. The equations governing relativity do not yield. Energy requirements climb beyond anything stars themselves can easily provide. Wormholes remain mathematical structures without physical evidence. Warp drives survive only as fragile theoretical possibilities surrounded by impossible conditions. The universe is not waiting for a clever enough species to bypass its foundations, but the light still arrives. Against every scale explored across this long journey, that fact remains strangely intimate. A galaxy unreachable by ship, unreachable by conversation, unreachable even by present knowledge, is still capable of touching Earth softly every clear night through the simple persistence of traveling photons. It made the crossing we never will. And perhaps that is enough, because somewhere inside the vast architecture of spacetime, among expanding galaxies and dark matter halos and stars burning toward eventual extinction, the universe produced at least one world where ancient intergalactic light could be noticed, understood, and quietly appreciated before disappearing forever into living eyes. Rest now,